Okay, welcome everyone to another MICCAI webinar. Today we're joined by Jun Ma, and I'd like to hand over straight to you so that you can introduce yourself.
Yeah, thank you. Hello everyone. My name is Jun Ma. Currently, I'm a postdoc researcher at the University of Toronto. My research mainly focuses on developing robust and accurate segmentation algorithms for various medical imaging uh, modalities and segmentation targets. Yeah, that's it. Yeah, should I start now?
Yes, great, thank you.
Yeah. Yeah, hello everyone, and yeah, first of all, thanks for the invitation. It's my great pleasure to be here to share our experience during the past 3 years of MICCAI FLARE Challenge. I'm one of the leading organizer of the FLARE Challenge. So today, my presentation will focus on the efficient practices in data management, coding, and visualization. So basically, FLARE Challenge we aim to promote the development of fast, low resources, accurate, robust, and effectual abdominal CT segmentation algorithms. So before diving into the details, I'd like to share several disclosures. So first, the shared practices are um, empirical, and they were mainly validated in abdominal CT segmentation tasks. But I believe many of these strategies can be be generalized to other 3D medical image segmentation tasks. Secondly, most of the credits belong to all the amazing participants in FLARE challenges. And thirdly, we received GPU sponsorship by NVIDIA in FLARE 2021 and prize sponsorship from Tanari and Pear in FLARE 2022. This is outline, and I will be starting with a brief introduction of the background, including medical image segmentation tasks, the current methodology trend, as well as the main motivations of the FLARE challenge. And then I will talk about the learned efficient modeling and coding strategies for abdominal organ and tumor segmentation during the past 3 years of MICCAI FLARE challenges. And finally, I'd like to share some efficient practices for data management and results visualization. So firstly, what is segmentation and why do we need segmentation algorithms? So basically, segmentation aims to delineate the boundaries of various organs and lesions or other targets that are interested to clinicians. So for example, by segmenting these organs in CT scans, we can use the results for the quantification of anatomical structures. And furthermore, by segmenting the lesions, we can conduct the diagnosis and the disease progress analysis based on the segmentation results. And furthermore, by segmenting the lesion organ and the surrounding tissues, we can use the results for treatment planning. So in a word, segmentation is a core technology towards precise medical image analysis. Currently, medical image segmentation is still an active research field. Here, I analyzed the word frequency of accepted papers during in MICCAI 2020 to 2023. So here are the 4 word clouds. It can be found that segmentation is the high frequency word during the past 4 years. And yeah, actually, segmentation is not a new task. It has a long history with half a century. Here is a brief timeline. At the very beginning, people usually used heuristic methods such as thresholding, region going, and so on. These simple methods mainly rely on naive image intensities. It is fast and straightforward, but it cannot handle complex medical images because the effect of the noise and inhomogeneity. From 1980s, with the development of variational models, segmentation is usually formulated as this kind of mathematical modeling task. Here, it's an energy functional of the segmentation counter, and then we will design some optimization algorithm to solve this minimization problem. The final solution is correspond to the segmentation counter. Variational models can incorporate various priors based on our understanding of the segmentation task, but it requires lots of high parameter tuning and cannot directly learn from the data. Starting from 2015, deep learning dominated this field. We have heard lots of popular networks such as FCN, UNet, DeepLab, and so on. The main advantage of deep learning-based method is that it can directly learn representations from the data in an end-to-end manner. However, these models are usually tailored for specific tasks or image types which have limited generation ability. With more and more powerful, more data and more powerful computing available, in 2023, segmentation enters the foundation model era. The milestone work is the well-known segment anything model, termed as SEM, which was trained on 11 million images and with 256 GPUs. Yeah, this is a clear segmentation method trend during the past half century. I'd also would like to briefly mention that why do we organize challenges? So we can see that algorithms evolve very fast, and new papers and methods are released almost every day in this field if we go over the archive papers. So, however, if the algorithms are developed and validated on customized datasets, it's hard to compare them in a fair way. So, to address this problem, organize widely used solution is to organize a challenge or set up the benchmark. So first, it has several advantages. So first, it can provide a fair platform to benchmark the same benchmark different algorithms on the same data sets, and which is relatively easier to identify the novel methods. And furthermore, it can help build a community around a task. Currently, these challenges or competitions have been the formal tracks on international conferences. We can say that MICCAI and Europe's, which are one of the largest conferences in the community, accept this competition or challenge tracks every year. So next, let's move on to the details of FLARE challenge. So basically, FLARE challenge was motivated by this question: is abdominal organ segmentation a solved problem? So here are so basically abdominal organ segmentation is the most popular challenge during the past maybe 10 years, and we have seen many popular benchmarks such as the liver segmentation task in leads, the pancreas and spleen segmentation task in MSD, as well as the kidney segmentation task in kids. If we look at the leaderboard for this organ segmentation, the top algorithms already achieved very high performance. It looks like this has been a solved problem because there is almost no room for further improvement in terms of the DICE score. However, these benchmarks have several limitations. So we found that although these algorithms have achieved unprecedented segmentation performance on this on these organs, we found that so first, most benchmarks only contain single center images. So we don't know how these top algorithms generalize to the unseen medical centers. This is because because images from new centers can usually have very different appearance because of various conditions such as the patient condition and the scanner condition. So, secondly, the ranking scheme don't take model efficiency into consideration, such as running time, GPU consumption. So this will guide most of the top solutions use model ensembles to boost the performance. However, model ensembles usually require lots of computing resources, making the algorithms impractical in real practice. So to address these limitations, we organize the FLARE Challenge in 2021. Our goal is to promote the development of fast, low resources, accurate, robust, and effectual segmentation algorithms. And for the fast, for each dimension, we designed several metrics. For fast, we evaluate the running time on the workstation. For the low resources, we evaluate the GPU and CPU consumption. And for the accuracy, we use a common dice score and normalized surface distance. And for the botanist, we include some unseen cases in the testing set to evaluate the generation ability of the algorithms. And finally, we require all the top solutions to make their code publicly available to the community and provide the out-of-the-box Docker container, so in this way, users don't need to configure the complex deep learning environment. They can directly use the Docker container to infer their own images with just one line of command. So in next, I'll just to give an overview of the task setting of our FLARE challenges. In FLARE 2021, it's a fully supervised segmentation task. We focus on these 4 organs and provide 511 CT scans. In 2022, we increase the number of segmentation organs to 13 and formulate the task as a semi-supervised segmentation task. And we provided both labeled and unlabeled dataset and invited participants to learn to design algorithms to learn from unlabeled scans. And last year, we further increased included the pan-cancer segmentation, abdominal pan-cancer segmentation task, and provide participants with partial labeled data. The goal is to segment the 13 organs and all the abdominal lesions in CT scans. Okay, let's first look at some highlights in FLARE 2021 challenge. So this is the first edition of the FLARE challenge. We focus on these 4 organs and provide a diverse dataset from multiple medical centers. And here are some visualized examples. It can be found that the validation and the testing images have very different appearance compared to the training set. This is because some images are from new medical centers compared to the training set. We designed this task to evaluate the algorithm's generation ability on these unseen centers. Compared to the previous abdominal organ segmentation competitions, the FLARE challenge has 2 main features. First, we provide a large and diverse multi-center data set. And secondly, this is the first abdominal organ segmentation challenge that focuses on both segmentation accuracy and efficiency, which means in addition to the commonly used DICE and NSD score, we also quantitatively evaluate the algorithm's running time and GPU memory consumption on the same workstation. Here are the final results, and the red score denotes that they don't have statistical differences. And compared to the previous start at that time, where the winning solution is 19 times faster, and it also reduced the GPU memory consumption by about 60%. So which are very impressive for us at that time. Here is the winning solution that developed a whole volume-based cost-to-fun segmentation framework. So it contains two stages. In the first stage, that directly resize the image to a fixed size of 160 by 160 by 160. In this stage, they ignore the physical spacing of these 3D scans and use a small network to directly segment the 4 organs. And then they use the segmentation results to extract the region of interest, which is conducted by cropping. And after cropping this ROIs, they perform used another network to perform the font segmentation based on this, which can, so by this cropping, they can include some unrelated background and focus on this for the target organs. After obtaining the segmentation results, they resize the image back to the original resolution and decropped to generate the results that has the same size as the input image. They used the unit-like architecture. The encoder module is composed of 2 radio convolutional blocks, and for this is very common, and there is no specific design for the encoder. But for the decoder, they separated the standard 3D convolution with kernel size 3 by 3 by 3 into 1 3 by 3 by 1 interslice convolution and 1 by 1 by 3 interslice convolution. This is the main design in terms of the network to improve the efficiency of the network architecture. In FLARE 2022, we made some changes to the competition, to a challenge task. So in FLARE 21, we have demonstrated that it is possible to achieve the good trade-off between segmentation accuracy and efficiency. But FLARE 21 only focuses on the 4 abdominal organs. In FLARE 22, we upgrade the task with 3 features. So first, we employed the semi-supervised task setting. The main motivation is that it's relatively easy to collect like, for example, 50 annotated cases, but it's impractical to label like hundreds or thousands of cases. So a straightforward question is, how can we use the unlabeled data to improve the model performance? So this is the reason that we set up this semi-supervised task. The second feature is that we increased the number of segmentation targets from 4 organs to 13 organs, which contains the main abdominal organs with various morphological features. For example, these organs are usually have the compact shape, but for in FLARE 22, we include some tabular features and some organs like duodenum, which has relatively complex morphologies. And thirdly, we use the more comprehensive metrics for the resources evaluation. In FLARE 21, we only evaluated the maximum used GPU memory. But in FLARE 22, we designed these two metrics which evaluates the whole GPU and the CPU consumption during the inference process. We count the error under this resources time curve. This is the challenge design. It contains a development phase and a validation phase. During the development phase, participants can access the all the training cases, including 50 labeled cases and 2,000 unlabeled cases. And they can evaluate the model performance on the tuning set with 50 labeled cases. During the validation phase, all the cases are hidden, and each team can only have one chance for submission to avoid overfitting the testing set. During the competition, we used 200 cases from multiple different centers for internal validation and then rank the results. And then we select the top teams to conduct post-change analysis. And specifically, we collected another 3 cohorts from North American, European cohort and ASA cohort, aiming to evaluate the algorithm's generation ability on these unseen images. Here are the results of we finally received 47 Docker submissions, and here are the results on the hidden testing set. So it can be found that this table lists the top 10 results. It can be found that most teams can achieve high average test score and NSD scores for these organs, and impressively for 3D volume with for large 3D volume, the top teams can finish the inference within 10 seconds and consume only around 2 gapped GPU memory. Here are the winning solutions that proposed an iterative set of labeling learning framework. So first, they trained 5 big unit models by cross-validation on the 50 labeled cases, and then they predict the unlabeled images with the model ensemble to generate the pseudo labels. And then they define this uncertainty score to select the high quality pseudo labels. So here for the uncertainty score, intuitively it measures the consistency between the segmentation results generated by multiple different models. If they have a high consistency, the uncertainty score is low. Otherwise, the uncertainty score is high. So they select this high quality pseudo labels with the uncertainty score and merge them with the labeled training set, and then repeat this process until the performance is saturated. And finally, they train a small N unit on the based on all the high quality pseudo labels during the iterative process, as well as the original 50 labeled cases. Here are the different settings of the employed big N unit and small N unit during training. So for a big N unit, they increase the number of convolutions per stage and the from 2 to 3, and the remaining settings are similar to the default unit. But for the small unit, the reduce the number of channels in the first stage from 32 to 16, and also reduce the convolutional numbers for to 2 from 3 to 2, and reduce the number of downsampling times from 5 to 4. They also use the relatively small input patch size and high inputs and low image resolution, and disabled the test time argumentation. Here are the performance during the iteration. It can be found that with the first iteration can significantly improve the model performance, especially for the small unit. And after 4 or after additional 4 iteration, the performance saturated. But the key conclusion is that the schedule labels can significantly improve the model performance. They also designed an efficient slide window strategy for the inference, which is based on the prior knowledge. So basically, we have a prior that in CT scans, abdominal organs usually located in the middle. So the strategy is very simple. If the middle window has no foreground predictions, they will skip the prediction process of all the surrounding windows, so which can reduce the computational burden. And we further evaluate the top 14 teams on the 3 external cohort, and so it can be found that all these teams can generalize well to the North American, European, and Asian cohort. And we also evaluated the fairness of the best performing 2 teams. It can be found that these 2 algorithms have no bias across these demographic features like gender, age, and the manufacturers. So a quick summary of the FLARE 2021 to 2022 challenge. So first, a small unit can achieve generative performance given around 200 labeled images. And secondly, efficient inference method. We can design efficient inference methods based on prior knowledge of abdominal CT scans. And third, it's possible to achieve a good trade-off between segmentation accuracy and efficiency, as all the top algorithms have demonstrated during the computation. And importantly, we found that unlabeled data can significantly improve the organ segmentation performance. So again, in FLARE 22 challenge, we only provide 50 labeled cases, and all the remaining cases are unlabeled. But we found that the top algorithms generalize very well on during the external validation. In FLARE 23, we further upgraded the task with 2 new features. First, we include the cancer segmentation task, and second, we provided unprecedented large-scale dataset with over 4,000 CT scans. Here are the results of the top 10 teams. Again, the red numbers denote that they have no significant differences. And here are the box plot to show the distributions of the segmentation scores on the testing set. So it can be found that for the organ segmentation, most of the top teams can achieve an average z-score of nearly 0.9, and they usually have fewer. The top teams usually have fewer outliers. However, for the lesion segmentation task, it's the top performance is significantly lower than the organ segmentation. This is reasonable because the lesion segmentation is a much harder task. And we can also find that these points, the results are scattered across the score range from 0 to 1, which means some their algorithms may fail on some challenging cases like the image with a small lesion. This is a winning solution, and actually it's also straightforward, and it didn't employ fancy network architectures. So basically, they still designed a two-stage framework, which is similar to the winning solution in FLARE 21. They first trained the UNet to predict to segment the ROI, and for this ROI, they simply binarize all the target organs into all the target organs, and this unit is just a two-class segmentation model. So after obtaining the ROI, they train another two networks to segment the tumor and organs respectively. To use the unlabeled and partial labeled dataset, they still use pseudo-label based method, which is similar to the winning solution in FLARE 2022. And they treat the tumor and organ segmentation individually with two different networks. And to improve the model efficiency, they introduced the multi-threading implementation and GPU-based pre and post processing method. I will mention the details in a later slide. And they also used the efficient sliding window strategy, which was developed by the winning solution from FLARE 2022. And so most of the winning solutions are built on UNet, which is the most commonly used segmentation 3D medical image segmentation network. For the default inference pipeline in UNet, in this case it cost 92 seconds, but after the optimization, they reduce the total time to around 12 seconds. So here they found that the resampling process consumes the most time, and the reason is that the default implementation used the scale image for the resampling, and the change is to the built-in touch function for this purpose, which is the touch dot interpolate. And secondly, for another important strategy to reduce the inference time is to use the slide window, use the efficient sliding window method, which was developed in FLARE 2022. It can reduce the on time from 13 seconds to just 2 seconds. The key point is to ignore the background regions during the inference. And another small technique is to switch the order of resampling and argmax. So basically, they first obtain the semantic labels by just using argmax, and then resample the label to the original spacing with interpolation. It can reduce the time from 7.6 to just 1.3. Here, let's make a brief summary. So far we have introduced the MICCAI FLARE task settings and the winning solutions during 2021 to 2023. And we have learned some efficient modeling and coding strategies for efficient abdominal CT. image segmentation. So the first strategy is to use the two-strategy framework. Since the data set the CT scans may contain not only the abdominal part but also the chest and even the leg part, or even the whole body CT scans. So it's efficient to use the localization and segmentation pipeline to perform organ or limb segmentation. So for the localization task, you can use a small network on coarse spacing or low resolution images. And for the segmentation task, we can use a relatively larger network and conduct the segmentation on fine spacing or high resolution images. And we also found that UNet and its variants are still efficient or effective architectures even in 2023. And UNet has been the most popular framework for the 3D medical image segmentation task, and which is also highly recommended if you want to enter this field. The code is really well written, and for students, it's also a good. I also recommend to go through the code report to learn how to write the. So at least for me, I learned a lot how to code based on the UNet repository. And another suggestion is to use built-in touch functions for pre-processing and post-processing. For example, the previous UNet used the scale image size function, which is time-consuming for the 3D during the inference. But by simply changing this function to the built-in function, touch built-in interpolate function, we can significantly improve the inference speed. And another small trick is to set an upper bound of the number of slices during each iteration of inference to avoid the GPU out of memory issue. And so we also recommend to use a built-in touch argmax function to avoid multiple data translation between CPU and GPU. Another useful strategy is to parallelize the following two processes. The first is read and process and data preprocessing. A second is to load. Load the model and use a small batch to initialize the touch library such as conv or nonlinear operations and so on. So these two steps can be parallelized. And finally, for the abdominal CT scans, it's if using the efficient sliding window based on the location priors of abdominal organs can significantly improve the inference speed. This efficient strategy is mainly focused on the model development because the challenge provides a fair platform for participants to develop and validate their algorithms. However, in real practice, especially for our own dataset, we also need to. There are another important task: data management. So we want to. So the key question is how to manage large-scale medical image datasets. First we command standardize the dataset in unified format. For natural images, this is very simple. We can directly use many open source packages like OpenCV scale images to normalize images into JPG or PNG format. However, for 3D medical images, data standardization is not that simple. Oops. Oh, sorry. Here, DICOM and NIFTY are two commonly used medical image format. And so DECOM is a comprehensive and standard format which are widely used in clinical settings, such as PACS in hospitals. It can contain lots of the meta information, but each file is usually only contains 1 2D slice, which is not very user friendly for in deep learning framework. In contrast, Nifty is a simple format, and one file can contain the 3D image intensity matrix and the necessary metadata. So in deep learning framework, we recommend using the Nifty format to prepare the dataset. But compared to the natural images, another important thing is to pay attention to the meta information, such as origin, orientation, spacing, or resolution. The origin refers to the reference point from which all voxel coordinates are measured. Typically, this origin is defined in relation to the patient's anatomy and the scan's coordinate system. Orientation describes how the scan is aligned with respect to the patient's body and the scan. And the spacing refers to the physical distance between adjacent voxels in the 3D volume. So for this metadata, we recommend to use the same orientations to prepare the dataset. And during the pre-processing, we also recommend to normalize the images into the same resolution. It's better for some for the small target segmentation. A second suggestion is to use the multiprocessing for data pre-processing. And here is an example to use a typical for loop to normalize CT image intensities to 0 to 555. It is fine. So it is fine to use this simple script to handle like a few hundred of 3D scans. However, if we use the same script to handle like thousands of 3D medical images, this will be super time consuming. Only once pre-processing step may cost 1 day. So to address this issue, we recommend using the multiprocessing, and it's not too hard to convert this conventional for loop to multiprocessing. We just simply import the built-in multiprocessing package in Python and convert this for loop to a function, and then we define the number of cores, which is usually equal to the available the number of available CPU cores, and use the following 2 lines to perform multiprocessing. An important tip is to store the data on SSD rather than HDD, which can significantly improve the efficiency. After finishing the data processing and the model development, the next step is results analysis. How to effectively visualize and analyze results. We usually use such figures to such segmentation overlay figures for qualitative analysis. For example, this is the image, this is ground truth, and here are the segmentation results of different algorithms. So to create such figures, and one commonly used software is ITK Snap. So we can simply drag the image to the here, and then secondly drop the segmentation results here. It can automatically generate this overlays. We can easily adjust the opacity, and here they also provide a button to create a screenshot of the segmentation results. So all these figures were generated by ITK Snap. Another commonly used software is 3D Slicer. It is also free and open source. In addition to visualization, it also provides comprehensive image analysis tools. Here is the list. Like it also supports lots of extensions. So in a word, if you want to perform relatively complex task or even want to incorporate your algorithm into open source image viewer, 3D slicer is a better choice. But if you just want to create some segmentation visualizations, ITK Snap is a better choice. And finally, I'd like to share some commonly used figures to visualize results. The most commonly used figure plot is dot and box plot. It can provide comprehensive descriptive statistics of the metric values of the algorithms. Here, each point denotes the performance on one testing case, and so with this figure, we can quickly have an overview of the algorithm performance. The second is bubble plot. It can display 3 dimensions of the data. For example, in this example, we can show the running time, dice score, and the GPU memory consumption simultaneously. Next plot is the statistical significance map. It can visualize the pairwise significant superiority between different algorithms. And here, the yellow color indicates that the measure score of the team on the x-axis are significantly better than to those from the team on y-axis. The blue color indicates no significant superiority. In this example, for the death score, all these 3 teams have no significant difference. And next figure is the blob plot, and it is very useful for ranking stability analysis. The x-axis denotes different algorithms. Y-axis denotes the rank distributions. The area of its blob is proportional to the relatively frequency of achieved ranks. So we can quickly have an overview of the rankings of the achieved rankings of different algorithms. The last figure is the red plot. It can allow us to compare multiple variables simultaneously. So this is very useful for visualizing the performance of algorithms across several dimensions. For example, here we can find that the identifier achieved the best death score, but it has very low overall rank because it didn't perform well on the efficiency matrix. For the first place, although it didn't achieve the best death score, it has a great trade-off across all these dimensions. To create this kind of figures, here are 2 recommended packages. First is ChallengeR. You just need to provide a CSV file, and it will generate all these plots and with a comprehensive report. The second recommended package is Plotly. They provide lots of great examples and user-friendly tutorials, so we can quickly generate this kind of figures built on their examples. Yeah, so finally, here are the take-home messages. First, we shared some efficient modeling and coding strategies for abdominal CT segmentation, such as using two-stage framework, touch building functions, especially for the interpolation, and also using the parallelism to simultaneously perform data loading and model checkpoint loading. And furthermore, we can use the efficient sliding window for the abdominal organ segmentation based on the location priors in CT scans. And next, we recommended 2 strategies to handle large-scale medical image 3D dataset. The first is to standardize the image into the commonly used Nifty format and use multi-processing to perform pre-processing if you have thousands of cases. And we also shared several commonly used figures for results analysis and visualization, such as So for IT Snap and 3D Slicer to visualize the segmentation results, as well as some commonly used plots to analysis the results, to analyze the results, and challenge R and plot are two recommended packages to create this kind of figures. Yeah, finally, please allow me to quickly end my presentation with two seamless advertisement. The first is we have launched the FLARE 2024 challenges. We provide over 10K CT scans for pan-cancer segmentation. This task focuses on all kinds of lesions in CT scans. And secondly, we organized a workshop on in CVPR 2024. The topic is about foundation models for medical vision. We also organized a competition about segment anything in medical images on laptop. And we have invited 7 esteemed speakers to give our presentation during this event. So welcome to join us. Yeah, and huge thanks to all my collaborators and my supervisor for organizing for their great support in organizing the FLARE challenges, and all the data code, the code of the winning solutions and their papers have been publicly available on the challenge website. And yeah, that's it. And I'm happy to answer any questions.
Thank you very much for this really interesting presentation. I'll stop recording now and we can take any questions.
Okay, yeah, thank you.